so much.
Welcome, sir. Sir, shall we start?
Yeah, why not, please.
Thank you very much, sir. And good morning to all of you, and welcome once again here on the same platform in the online 5-day online FDP on novel materials at SRM IST Ghaziabad. And today with us, Dr. Asad Noor Siddiqee. He will present their views on the high entropy alloys. And Dr. Siddiqee have received his bachelor degree from Government Engineering College, Jabalpur in mechanical engineering, and master and PhD degree in production engineering from Department of Mechanical Engineering of Indian Institute of Technology, Delhi. He is currently working as a professor in Department of Mechanical Engineering at Jamia Millia Islamia, New Delhi. His broad area is in production engineering, and specific area includes friction stir processing and welding, material technology, and structural property correlation. He currently handles the Center of Innovation and Entrepreneurship and is a key contributor to the draft startup policy of Jamia Millia Islamia. He has supervised several PhDs and has published more than 175 SCI journals, publications, and a number of books. He has applied and received a number of patents. He was invited as a visiting professor at Advanced Manufacturing Institute of King Saud University of Kingdom of South Africa, Saudi Arabia. Alongside KSU, he has also developed active working international cooperation with Wenzhou University, China, and Samara National Research University, Russia. So this was the brief introduction about Dr. Siddiqee, and now he is here with us to present their views on high entropy alloys. Sir, thank you very much, sir. Sir, your mic is mute, sir.
Okay. Thank you very much, Gyanendra-ji. I must thank the organizers, including the host of the meeting, as well as the SRM University, for giving me this chance to share my views with you. So thank you for the introduction, and I'm humbled with that too. I think I must straight away share my screen with the PPT. I believe you are able to see this.
Yes, sir.
I believe you are able to see this. Okay, thank you very much. So, at the outset, I must give you a brief background of this high entropy alloy, and I will take you through the journey of materials, how and why the materials have evolved. Because there is no change without any driving force, and as far as science and engineering is concerned, the only and sole driving force remains the energy. Energy. Every system that comes to operation actually follows the law of minimum energy. That's why the change takes place. The moment you change the state of any system, it responds in order to keep its energy minimum. This is so general a statement that it applies to HEA also. How it applies to HEA that we will see through when we go ahead with this presentation. But as far as mankind is concerned, the driving force is different. The nature has its own driving force, that is energy, minimum energy. Why the system has to respond is to keep the energy minimum. But why the mankind actually is so much engaged with the nature has a different reason altogether. And what are all those reasons that we go through this interesting journey of materials, and we will end up with HEAs. HEA meaning high entropy alloys. Materials and alloys typically are conventionally driven by enthalpies because it follows the Gibbs rule. But in case of high entropy alloys, they actually play with the entropy rather than enthalpy. That we will see it later on. But in any case, this class of material is the most recent one. Most recent one means you can imagine that the bulk of literature has started coming. The bulk of literature has started coming only in the early past decade, that is the 2020s and 2011 onwards. So my presentation will be such that, because I can see that there are 72 participants, and I am very much sure that not all of them belong to coal materials. So, keeping this in view, I have kept my presentation or talk, whatever you call it, to be so general that I will be able to engage with all of you, whether you are from materials or any other stream, because the HEAs mainly is a core materials, belongs to core materials domain. So I have kept,
relative
so I have kept my presentation engaging to all the participants, and to my own interest in HEAs briefly. I must say, at this moment, share with you that I am now working corely in the materials development by FSP, frictionless processing route, and mostly the composite development and the functional material development, including metal forms. And of late, we have also ventured into development of alloying, direct alloying. So we have actually developed a few alloys also through frictionless processing purely without involving any other process in that. And our recent publication in materials letters that is available online also, that is actually the multi-component system alloying through FSP, purely FSP. That is the first paper that actually reports findings on a multi-component material system that has been developed purely by the FSP. And we have recently been able to produce medium entropy alloys purely through FSP, and the high entropy alloy work is in very advanced stage of being reported to a journal. So this is my interest actually. What way I engage with HEAs is this. So let me come up with my first slide. Since it's a journey, so I will begin with the evolution of mankind on this planet. Just to keep you engaging, I would also like to mention here that because I am into core research in materials, but doing research is interesting, but sharing research in terms of presentation is very boring, at least to those who are listening. So I will not go into the much details of research aspects, and those who are interested in this particular material, they can pick up their own specific domain where they can actually, where there is a scope for them to enter. So the earliest historical evidences of mankind exist since the Paleolithic age, and the Paleolithic age, the main material of use was stone, and the main driving force why the mankind engaged with the tools and materials was to have food. Just they were interested only in livelihood. This is what is the early Homo sapien mankind. You can see that the Homo sapien mankinds had to have very big tummies like the silver line gorilla today. Even today it has, but it has very small brain. You can see that. So this is the early phase of our evolution, and wherein the Homo sapiens used to have a very large, big tummy and a very small brain. Why they did have such kind of feature is that they used to eat actually. They used to eat everything raw. Whatever is available comes to their way. They used to eat it raw. And together to make that available edible material to be able to be to consume, they used to have a lot many number of tools, and these are all the tools that they used to have that point in time. So these kind of tools, if you see that these tools mainly made of stones, and their geometry is comparable to the tool geometries as of today. Because my interest is also in metal cutting, so I can actually relate you with the geometry of these tools with the single point cutting tools. It is not very much changeable in terms of tool geometry and material properties. Anyways, they used to have these tools to make these edible materials worthy of consumption, and then when they used to eat it, because these were raw, so they required a lot of energy for digesting them. That's why most of the blood flow was into their stomach, and they used to have a tummy, very great tummy. And naturally, when the blood supply to the stomach is more than the brain, then their brain used to be very small, and they could not think very advanced. Later and later, they evolved, and they actually started building developments, and this is one of the earliest evidences of the temples of Gojo that was purely made of steel. Then there comes a time, then there came a transformation. They suddenly invented fire, and somehow the accidental fire, some of their edible objects were cooked, and when they consumed that cooked food, it actually have a positive effect on their stomach as well as to their tongue taste. Then they thought that this is a very useful item, and they started to control the fire. So they somehow they make the fire, and then they used to keep it alive. Akhand Jyoti jisko hum kehte hain. So they used to do everything to stop it from getting put off, and this is dates back to the evidence of this is seen somewhere date back to 45,000 BC before Christ. Let me maximize this. Okay. So usually in the modern day time, people say that revolution began with the invention of wheel. I would say it the other way around. The revolution began with the invention of control of fire, because this actually put a very small stress on their stomach, and by virtue of which the blood flow to the brains started rising up. This actually expanded their brain, and that actually resulted in the later development. So with the invention of fire, then they used to use other materials, and the Neolithic ages, that means the end of era of Stone Age, when they used to keep fire on some materials, suddenly they realized that some of the materials on which they are lighting the fire, they turned into metal, because they actually eventually burned the fire on the ore. And this is why they actually invented the bronze, and then they enter into the bronze era. This is how they enter into the bronze era, and when their brains developed, they actually started thinking creatively, and they started using several other materials for use it includes stone, wood, clay, and art, and they even used to prepare the artifact. And then came another revolution after the control of fire. There came another revolution, that is the wheel, which actually energizes the journey of development even today. So this invention of wheel dates back to 5,000 BC from now. That is the 7,000 something BC, 7,000 years from here. Then came the era of, after the Stone Age, then came the first era of Bronze Age. And because the people have learned that there are materials which are other than stone and that can be developed by use of fire. And then they actually started searching for the materials which actually can give way for the metals, that is the bronze, the only material known to them. Now, they actually eventually located the mines for the copper ore, and this is the mine of copper ore 5,000 years BC in now modern day Israel. This is the 5,000 BC copper mine. Then when they invented new material that is known as the bronze, then they started using their brain articulate. They actually started making the art such as this one that is known as bronze standard, which was used to keep at the headrest of the dead bodies of noble person. So this is one of the earliest forms of the standard that was actually laid with the coffin of one of the noble person, Ankara. Then they actually, their mind actually developed, they started thinking in the destructive direction also, because it increased their greed, and then they started making lethal weapons. This is some of the examples of the early days of bronze weapons and weaponry, as well as the armors. This is the bronze armor, and these artifacts and articles dates back to 1500 to 1300 BC from now, and these objects were found to be located near the France. Somewhere that time also, now because their brains have grown a lot, and then they started engaging with the materials, and that way they started progressing. Then they moved towards civilization. One of the earliest days of civilization is the Vedic Age, that is found to be near Indus Valley. It is around 1500 to 500 BC. This is the excavation site of Indus Valley civilization. And when the wealth increased with the civilization and materials, as the wealth increased, then they actually resorted to the wealth management also, and then that gave way to the trade. And this is the most early stages of the Indus balance. This is the balance. Now the thing is that I must also mention here is that on this planet, the most important resource of all the resources, that is the natural resource, is the mankind. Why mankind? Because it can think, whereas other resources can't think, whether living or non-living. So among all resources, the most important resource is human. And at the disposal of human, there are again many number of resources which actually can be consumed by the human. And out of all these resources, every other resource other than time is limited. Although it is abundant, but limited, time is limited. Why the time is limited? Because one's own life is limited. One more thing I must tell you at this point in time, most important resource is human resource, and most limited resource at the disposal of human being is the time. And it is most precious also. Why most precious is that it is limited. It comes free. Anything which comes free, actually that is very poorly handled by the mankind. So it is coming free. It is although limited, but it comes free. So we are wasting it like anything. The third point here is that whereas every other resources can be recyclable, time cannot be recyclable. This makes it most precious at the hands of humankind, and at the same time, it happens to be the most poorly handled at the hands of humankind. I still remember one story when my teacher used to tell us about Faraday, Michael Faraday. That story goes like this. I am telling you the importance of time because we are all the ones who actually waste time like anything. So Michael Faraday, one fine day, one professor came to see Michael Faraday to his lab, and when he got down at the tram, out of the tram, and he caught a Tonga. Then the Tonga person told, "Where do you want to go?" Then he told that I want to go to that place. Then the Tonga fellow, he refused. But he told that, okay, I'll not go there. Then the professor told, why will you not go there? Then he told that, see, if you take me there lives Michael Faraday. He will catch hold of me and then he will engage me within his lab and I'll get a Nobel Prize. That's why I will not go to that place. It's a joke. But anyways, when he went to meet Faraday, then he was very angry with the Faraday. Faraday did not understand what is going on. Why is he angry? Then he told, see, some days back I saw a news in the newspaper that Michael Faraday wrote to the Queen Victoria a letter. And again, I read in the newspaper that Michael Faraday wrote a letter to the Royal Society, London. Then I thought of writing a letter to you, and you never responded. I wrote several letters, but you, despite that, you did not reply to me. Then Michael Faraday told him, he told that, I'm sorry, professor, to have you annoyed, but I must tell you that I have everything in my life. And only one thing that is limited with me is time. Because my life is limited. That's why I don't write letters very often. But when the Queen Victoria offered me knighthood, I simply denied. And when I denied, it made a headline. Then came the Royal Society London. They offered me presidentship. I also denied to them. Then again, it came the news. That's how I write, but I don't write because I have limited time. So this is the... So next material in evolution was the gold. And people used to have gold mask in the early days. This is one of the example of the mask made of gold. And it actually belongs to the Greece, 1550 BC. And this is a gold helmet. It belongs to Spain. And then these items are aristocratic items. See, this relates to trade. This relates to battle and war. This relates to battle and war. This relates to aristocracy, but this relates to knowledge. This is known as sky disc, and it was made of brass, bronze, gold. Multiple material at the same object for the first time were reported to be found in 1550 BC in Germany. And this, what they call, is the sky disc, because most of the features that were visible in the sky during the night time and daytime, both were clubbed together and converted it into discs. So this is one of the scientific artifacts of that point in time, which involved materials which were multiple in nature, including gold, bronze, and brass. This is the welding era, and these are the bronze tools, द्वापर युग के bronze tools हैं, जो कि agriculture फ्यूचर में ये फरसा आप देख सकते हैं, ये आप स्पीयर हेड देख सकते हैं, एंड डबल साइडेड डबल एज तलवार आप देख सकते हैं. These are all, they belong to bronze articles in the Vedic age. Next came, this is what is the development of the Bronze era, Bronze Age, which actually began somewhere around 3500 BC and it continued till 1600 BC. This is the time duration. 3600 to 1600, 2000 years on the planet actually reigned by the bronze. Then suddenly came the material known as iron, and it dates back to 1600 BC, and its history actually goes back to Turkey, today's Turkey, Anatolia. Today's Turkey, this is the sketch of the then used iron metallurgy that was prevalent in Turkey. So the Iron Age began after the Bronze Age, and you can see that the driving force of materials evolution were development, then the wealth, and then the power and aristocracy. These were the driving forces for the development of materials. Development like civilization, wealth like gold mass, and helmets, and the power, these are the articles of power, related to power, which was actually for supremacy and aristocracy. Next came the age of Iron Age, and Iron Age, the first, because now, see, from where does the wealth come? In the Stone Age as well as in the Silicon era today, the planet remains the same. But we have a lot of development today. We have flying objects, we have very nice roads, we have bullet trains and all. Why suddenly this value creation, from where does this value creation come? It has come from the brain. It has come from the rightful engagement of the human resource with the rightful use of time at the hands of human resources. Otherwise, everything else, the same planet we are living on, but the wealth creation, the value creation comes when human being or the human resource engages positively. So as the brains evolved, and then first came the currency concept, and it dates back to Persian Empire, who actually developed the currency in terms of gold coins, and they introduced this gold coin as the international currency. And at that point in time, Persian Empire actually reigned until the Khyber Pass. So these are some of the earliest examples of international currency. Then came, because the mind evolved and the civilization started people to think in a positive manner, then came the first literal word, artwork, that is by Panini. He who actually described the grammar and morphology of Sanskrit. This actually dates back to 350. This is the evidence that has that dates back to 350 BC, which actually describes the work of Panini, and who actually invented the grammar and morphology of Sanskrit language. Then suddenly came 500 BC was the invention of cast iron. It was accidentally discovered in China. They were working on bronze, and they actually working with fire and the bronze ore, and they put fire on bronze on certain stone. That actually stone happened to be the iron ore. They are actually accidentally, when the iron ore met with the fire and the fluxes used for the bronze material, then they suddenly discovered the cast iron, accidentally 500 BC. This is the a sketch of the initial cast iron which was discovered in China. Now, as the world actually grew up, then the materialism also grew up. That gave way for the spiritualism, and then came the era of Buddha. Because as the wealth grows, it actually brings in the materialism. Lot of fight, power, greed, these things enhance. When these things enhance, then suddenly Buddha, actually Gautam Buddha, he actually renounced everything because he belonged to aristocratic family, but he could realize that there is nothing in this material world, and then he propagated his own doctrine. Although those doctrines could not be recorded at that point in time, only after Asoka, who later on turned the disciple to Buddha, he actually started building work of Buddha and came to be known. This is one of the earliest stages of the artwork. Then grew the artwork. This is the Ashok Chinna. And the first alloy, concept of a proper alloy, lies straight in New Delhi, that is in the form of iron pillar. This is the first on this globe, on this planet. This is the first evidence of corrosion resistance steel. I must tell you the background behind this Ashoka Stamp. This Ashoka Stamp was actually made by additive manufacturing. I must tell you, once I invited my friends in Russia and China to my university. I hosted them for 1 week. The Chinese fellow, that is Chiang Chen, he works on additive manufacturing. He was delivering a talk on additive manufacturing, and he told that it is the most recent development in manufacturing technology. Then I stopped on the dais. My supervisor, Professor Sunil Pandey, was also sitting on the dais. I stopped him, then I sought an excuse. I told that the history of additive manufacturing dates back to 345 BC, and the evidence lies right here in New Delhi in the form of Ashoka Stamp, or in the form of iron pillar. This is actually near Qutub Minar. So this was built by forged welding additive manufacturing technique. So it was one layer after the other, one layer after the other. It was actually forged, beaten, and then it was developed. So this is how it was. People say that the clay platform used to be raised as the height of this iron pillar grew, and those who were building it, they actually built it by forged welding, depositing layer by layer. So this is how it was built, and its properties are such that it is so alloyed that it stands from 2,500 years since then it was built, and it did not corrode. It does not corrode. I still remember when that scientist, his name is, the physicist who died 3-4 years back, is from UK, who was fully paralyzed and who could talk and hear by machines only. Can you name any one of you? This question I asked you just to see how many of you are actually present in there.
Stephen Hawking. Stephen Hawking.
Is anyone there? हाँ, मुझे लग रहा है कि only Gyalendra ji is there or what? I still remember when the test was in Delhi. You know one thing, when you go to Qutub Minar, you will see ramps being wooden ramps. You will see the wooden ramps. So those wooden ramps were built for the Stephen Hawking. He expressed a desire that he wished to go and see the iron pillar, and he wished to analyze what is there in that material which actually stops in rusting for as long as 2,500 years. Then he went there because that is a heritage site and no construction is allowed there. But for the wish of Stephen Hawking, there were some ramps built, and when he went to see the iron pillar, then he scratched some material from there, scraped by scraping. He scraped some material. Only person who is allowed to actually tamper with the material was the Stephen Hawking. So he scraped some portion and he took it along with him for the analysis. So this is the history of our civilization. So this was the materials development that is associated with India during the times of Maurya dynasty. Then came the landmark change. That is, the systematic book on metallurgy was published by Vannocchio in Italy in 1540 AD. AD, not BC. This is the most modern. This is the ancient era, and the modern, the medieval era belonged to 500 BC to 1500 AD, and this is actually a modern era because beyond 1500 AD is the modern era. So 1540 modern era, first book on metallurgy came up, and the quest for knowledge. See, this era was all about materialism. Around 500 BC was materialism. And materialism gave way for the renunciation. And the renunciation gave way for knowledge creation. This is how we evolved. Now we shifted from the materials era to the renunciation, and then renunciation gave way for knowledge creation. As a result of that, we came up with some spectacular work on metallurgy, and then the vulcanized rubber that was invented in America in 1839. This is the actual depiction of the early stages, not the original, but the early stages of vulcanizing in rubber, because the first photograph was shot in 1826. So this is, of course, this does not belong to 1839, but later. Then what was the driving force for evolution of the medieval era was this? The driving force was wealth creation made way for the wealth management. The currency, international currency, banking system, taxing system, these were all introduced during the 500 BC in the Iranian Empire. That enhanced the materialism, that gave way to spirituality during the time of Vedic time also, that the Lord Krishna came, and then after that Buddha came. Krishna, after Lord Krishna departed, 36 years after that, Kali Yuga started, is it not? So it was the overlapping period, the end of Bronze Era. It was the overlapping period, and some people multiply the years with 3,600 years, that will convert the Yuga into some galactic times and all. Anyways, but let's not go into that. So the wealth creation led to wealth management that actually enhanced the materialism because accumulation of wealth came in there. Once the management is there, then the accumulation is there. That enhanced the materialism. It gave way for the spirituality and then gave way for the knowledge. Spirituality actually gave way for knowledge, and all these developments suddenly start coming. You will see that the early modern era, 1550 and later till 1950, most of the inventions were during that period, 150 years ago. Then came the 1800s AD acid battery, for the first time used by Volta in Italy, and then the solar cell in 1883, solar cell again in Volta, Italy, and then the thermite welding. This is how we evolve the materials. These materials, actually, these evolutions always were assisted by the evolution in materials. The iron, the rubber, then the copper zinc battery, then the solar cell with the invention of selenium, and then thermite welding, magnesium, and many other things came into being. And then for the first time, 1912 AD, SS was invented in the Sheffield, UK. And then with the advent of germanium, the solid state electronic devices started coming into being. That is 1947, Bell Laboratory, USA. And then CNT, latest development is the CNT carbon nanotubes, and graphene. It was developed in 1991 by Lijima, Japan. So this is the modern story, modern day life. This is how we have now come up to. Now all these things, actually, you see the rise of knowledge. Once the rise of knowledge was there, then the supremacy came into being. Who is bigger? And the supremacy, actually, the quest for supremacy was actually the reason for the new development. What new we can do? Innovation. That's what we call it, innovation. The one who possesses the greatest knowledge will innovate better. And the very first innovation came in the form of materials. I will show you some very interesting facts about the materials. This is the story of 1550 BC, Daedalus and Icarus. These two were the noble person in Crete, in Crete, Roman Empire. And they were a very noble person. They were supposed to possess huge knowledge. And because of their popularity in terms of huge knowledge bearers, noble person, the Daedalus and Icarus were imprisoned by the empire, by the emperor. Then what did they do? They invented wing. This is the pictorial depiction of the wing. So it is said that mythologically, it is said that Daedalus and Icarus, when they were imprisoned by the emperor, then they invented wings to escape the imprisonment, the prison. And they invented wings which were which could be fully marked like the birds. And the material was fully biodecomposable, and it was free of any knocks and cocks, and the structural joints were made by adhesives. So this is what is the wings of Daedalus and Icarus. When the Icarus made the wings, then it was worn by his nephew Icarus, and he began to fly, and he could fly so near to the sun that his uncle used to say him, don't go so far, don't go so far, otherwise you will get burnt. And eventually his wings were burnt, and then he had to fall down to the earth. This is the mythological story, dates back to 1500 BC, that actually has the evidence till now in terms of engravements on stones and all. The diving force was the mythology. As far as back as 1500 BC, they could think of even flying object. Then you must be knowing one very important story of Timbuktu. I still remember my grandfather, when I was a small kid, he used to bring one wooden horse, and then when I used to sit on the wooden horse, he used to sing a song, Chal Mere Ghode Timbuktu. Chal Mere Ghode, maybe some of you might have listened to this kind of a story. So this dates back to Timbuktu in western parts of Africa. This dates back to around 700 BC, 700 AD till 1100 AD, so recent. So what used to be there in Timbuktu was that it was actually known for a salt. Ample of salt was there. So at that point of time, salt was very precious material, very precious material. So from all over the globe, people used to carry gold, and they used to exchange gold with equal weight of salt. So they used to carry 100 kg of gold from, say, India, and they give 100 kg of gold to Timbuktu, and from there they used to bring the 100 kg gold of salt, 100 kg of salt. Salt was so precious that the Dandi Yatra Gandhiji had done, because it was taxed, salt was taxed. So it only matter of time, different material have different value. At that point in time, the salt was having greater value in comparison to gold. So this is a very interesting story that is not very far from here. It is after the death of, after AD, the 700 to 1100 AD, this trade was very common in Timbuktu. So next, another important story was the Genghis Khan and samurai story. It was 1200 to 1300 AD. And when the Genghis Khan is a person who is known to have almost won the entire planet. But he was, when he was actually about to go to Japan for a fight, for a battle, because by that time he already won over the Chinese Silk Route of China, and then South China Sea. He tried to enter the South China Sea to take on the Japanese. Then at that point in time, the samurais used to be the fighter for the kings of Japan. And I must tell you that since the very ancient time, Japan does the reverse of what the rest of the world does. So when the Japanese king heard that, okay, Genghis Khan is coming, then he called a samurai. He called samurai. And he told that, see, Genghis Khan is coming, now you have to prepare yourself for fight. Then this is the very first, the very original sketch of samurai. They are building their sword. So samurai analyzed, okay, what is the strength of Genghis Khan. Then they came to know that they have a very light bow and arrow, because they make it by the tendons of the animals and the wood, that is the composite material. And so it was very light in weight, but their sword was very, very hard. And because it was hard, it was very brittle. So they make it very, its cross section very robust. So very heavy. Now the thing is that the Mongols have a very huge and hefty skeletal bone skeleton. So they could actually afford to have very heavy sword. But the Japanese have very small, very weak structure, small structure, bone structure, they cannot. So what they did is that they saw that, okay, the Genghis Khan's sword is hard, they will make it soft, because they always do the opposite to rest of the world. So they made it soft. When they made it soft, it was having very tough and ductile, but did not did not possess ability to cut. Then they invented carburizing. This is how they invented carburizing. This is what the summary is carburizing actually. So the carburizing in the material science we actually see has the history dates back to Genghis Khan samurai engagement, which actually did not take place because that point in time, I think first this thing ocean storm came, and then he had to go back without a fight, Genghis Khan, and they were saved. So this is the history of carburizing. Again, a fight. The driving force was supremacy. Then came another fascinating story is of Napoleon. You know, Napoleon used to have the costliest copy at that point in time. Because his journals used to eat in gold, and lower rung journals used to eat in silver plates, but Napoleon used to eat in aluminum because at that point in time, aluminum was the most costly material, costlier than the gold. You see, as date back as old as 700 to 1100 AD, the gold was cheaper than salt, and aluminum was costlier than gold in as late as 1891, because the aluminum was very white, and white has a craze. Everyone wants to be fair. Like there is a story of Queen Victoria, who was the queen of whites. So naturally, she used to look whiter than whites. Then she used to apply zinc powder, lead powder to look white. Then its skin was had developed cancer. To hide that cancerous marks, she used to started putting up more powder of lead, and that way she was turned into a devil. So this is the story of materials. So that point in time, aluminum was costly material. So the Napoleon III, not Napoleon Bonaparte, because Napoleon Bonaparte died in 1821, and the aluminum could be extracted from the ore only in 1824. The Napoleon III used to have crockery made of aluminum, and even his crown also studded with precious materials on aluminum. These are the actual artifacts during the time of Napoleon. Okay, the driving force was aristocracy. Again, when the knowledge enhanced, then it again led to aristocracy, aram, asayish. So aristocracy was on the rise. Now you will see that all these emperors and kings, they actually released on the development of the material. Now coming to, because I have 30 minutes, so I have taken too much time now. I'll hurry it up and then come on to the HES. Next, this is 1891. Then came the innovation led by Wright brothers. They invented an aircraft in 1904, and it was 100% wood. These are the Wright brothers. It was 100% wood. Now, wood had its own problems because its weight is a problem, its hygroscopic nature is a problem, durability is a problem. And all coverings were cloths, and main structure was the wood, 100% wood. So it has a problem, but they showed the way for the world that, okay, we can actually fly. Icarus Daedalus, they actually derived their idea from the Icarus Daedalus, and they invented a flying machine, 100% made from wood. Now the success of the flying object made by the Wright brothers led to a proper aircraft that was 100% steel, and it was all steel aircraft, Germany. Now, because the steel has durability problems and the weight problems, then came, because by that time, the 1924, the duralumin first age hardenable material was developed. So this is the all duralumin aircraft that is known as the Junker 17, and it is the first use of age hardened material known as duralumin for aerospace applications. Next is the all alloy material, 100% aluminum alloy. This is the evolution of the current day story of the aircrafts. So 100% aluminum alloy, different aluminum alloys, including age hardenable and non-age hardenable alloys. But as on today, for the last 10 years or so, the composite materials usage is enhancing and the aluminum usage is reducing. Now, there is a driving force, technological. Now we are living in the era of supremacy, and we continue to live in the era of supremacy. Now the driving force will always remain supremacy. Now this evolution actually has a reason with driving force, that is the technological supremacy and global strategic market, wealth and technological supremacy. Objective: high specific strength, durability, fatigue resistance, and toughness of airframe structure. This is the main objective. Why the material from wood change to steel to duralumin and then to the sundry of aluminum alloys. So this is the story of aerospace, and because the HEAs actually relate to aerospace. Now, the future of electronics, you see now, the future of electronics will look like this. The future flying machines, prototypes tested, will look like this. Future means maybe around 10 years going forward from now, not very far. Here's the future flying machines that will look like, and this is the feeder channels for the aircraft. So this is the multi-modal system, air to road, road to road, and water to road. These are all the vacuum tube transport that connects the offshore airports to the land-based terminals. And this actually looks like a typical airport of future. Recently, China has already cordoned off 3 square kilometers of Shanghai airport, and then it builds a maglev station with the 10 lanes in Shanghai airport. Now it is open. It was earlier cordoned by the architectural structures. Now it is open. So I must tell you that the maglev used to pass under the highway, 12-lane highway. So they could actually 6-foot concrete roof. They actually casted as underpass below the highway. Why that thick slab was casted at the roof of the underpass was to avoid the vibrations that is coming up from the highway. So this is what they are doing now. So this looks like the future airport. Now, what is the driving force now? Energy efficiency. The objectives changed now because we have put a lot of stress on the planet Earth. Then the people started thinking of energy efficacy and the time saving, because ultimate aim will be the time is the most precious things. The main driving force is the faster travel and the energy efficacy, and the objective is interconnected transportation with zero emission. Newer systems. This is the materials story. 1700s. It was all wind and hydro energy. Then came the mechanization in 1800s. Mechanization of printing press first was developed by the Thomson and Thomson, and then it came the power loom in Manchester. The power loom in Manchester were mechanically powered, and it dates back to 1860, somewhere around that. Then came 1900, this is the Ford car, 1909. These are the materials, now the materials of future. You see the rare earth material and transition elements are going to be on the rise now. The early transition elements and the later transition element on the periodic table. So this is the material projections for future. Driving force will be now the next development will be powered by the sustainable development goals of the future, because now the world body has come up with a lot of effort with regard to the greening the planet. So they have set up some sustainable development goal that have to be complied with, especially by the transportation sector, because the greatest amount of material being consumed belong to the transportation sector in terms of weight, in terms of volume. Among the greatest one is the air transportation. You see how much is the weight of 747 Boeing? It is 6 lakhs kg. 6 lakhs kg weight object is flying. So the weight of the empty aircraft without fuel is more than 6 lakh kg, and it can carry a weight hardly not greater than 1 lakh kg. So this is the dead weight of an aircraft which flies. So huge amount of material actually is involved in there. So the reduction in CO2 emission, they have set deadlines per passenger per kilometer, a 90% reduction in, this is the target, 90% reduction as a vis-a-vis, that is today, 90% reduction in NOx, and the noise emission reduction by 65%. Now you can see where you can actually have your own share of research. You can think of working in damping materials, damping of noise and vibrations, those who are in design and all, and how those who are in thermal side, they can think of reducing NOx and COX. Air vehicle design and manufacturing to be recyclable. This is the sustainable development goal for aeronautics. All air vehicles must be designed and manufactured from materials recycled, and out of which the Europe has taken the lead in this and has become the center for excellence for the sustainable development. Now the safety goals for the aircraft have also been set by the SDGs, Sustainable Development Goal. These are these. So the future requirement of material and design both will be governed by the SDGs, Sustainable Development Goals, to take care of the planet Earth. Now, what are all the challenges? The challenge is the fuel efficiency. Now, how come the fuel efficiency will come in the transportation sector? It will be the reduction of parasitic drag, and it actually has a design problem. You design the superstructure and the airframe structure, corresponding airframe structure, which minimizes the drag and reduces the fuel consumption, and then the weight reduction. Then the weight reduction directly relates to the newer material development. Superstructure, of course. And then the engine efficiency, the high temp engine efficiency solely depends on design of the engine, and the design of engine, the material used in the engine. So there are two aspects. High temperature materials need to be there. So the two materials for the weight reduction and the two materials for the material for weight reduction belongs to superstructure, whereas the engine efficiency material refers to high temperature, high performance material. Actually, the HEA fall into this category, and the tighter clearance between the engine and casing clearance should be tighter, very small. Greater is the smaller is the clearance, greater will be the engine efficiency. higher the temperature, higher the temperature, the engine and engine blades can withstand, better will be the engine efficiency. So the ultimate objective for engine efficiency will be the development of high temperature material and tighter clearance. The synergy then comes next is the synergy between the design and light and strong material. Now you develop light material and strong material, you design new designs. Now they have to, you should be able to manufacture with those material in those designs. So there has to be a synergy between design and light. So here comes the manufacturing aspect. This is the material aspect, this is the manufacturing aspect. Then can they adapt the manufacturing technology for new designs and advanced materials. So basically this relates to newer forming and joining techniques. So there is a lot of scope in materials development, design of objects, and development of new material for superstructure, development of new material for high temperature applications, and the manufacturing processes to deal with those designs and materials. So this is what is the future challenge. Now, the main object superstructure for the superstructure is the weight reduction, and the weight reduction actually directly relates to the specific strength of material. Typically, the conventional strengthening comes with these four aspects: refinement strengthening, that is dictated by Hall patch effect, and the strengthening by cold work, that is actually facilitated by enhancement of dislocation density. If you look at the fully annealed material, it will have the 10 to the power 8 dislocation density, and when you give it to heavy cold work, it will increase the dislocation density to 10 to the power 12. So this is the order of dislocation density that changes as a result of cold work. So cold work actually enhances dislocation density, which in turn enhances the strength of material. The first one is refinement strengthening, grain refinement, of course, Hall patch relationship, strengthening by cold work, that is through dislocation density. Then the solid solution strengthening, that is the resistance by lattice distortion and penning effect. The solid solutions that the foreign atom goes into the alloy will be either smaller than the parent or the solvent atom or smaller. So it will replace, but it is, if it is so small that it can be housed in the interstice, then it will be the interstitial solid solution. So in all three possible cases, the distortion in lattice will actually affect the dislocation movement, and hence it will strengthen. The next is the heat treatment. The heat treatment, these are the four basic conventional routes for strengthening. Number one, refinement. Number two, cold work. Number three, solid solution. Number three, heat treatment. Heat treatment, there are two types. One is the typically relates to steel. Then each micro constituents have their own properties, because of which they have their own contribution to the alloy. And it actually alters the property. In case of aluminum, age-hardened alloys, the precipitates, they are the finely dispersed dense precipitate that actually offer pinning. Through pinning effect, they offer the movement to, they offer the resistance to movement of dislocation. So that way, they again strengthen the material. So these are the four conventional routes for the strengthening. But the problem with these strengthening routes is that there is a trade-off between the strength and ductility. If you increase the strength, the ductility will proportionately go down. So that has to be, that is actually the basic limitation beyond which you can not go for a strengthening, because ultimately the ductility will not be sufficient, which was actually desired for the in-service condition. So this is the superstructure, airframe structure and scheme. But what about the engine materials? So engine materials, single crystal cast. You see, if those who are aware of the turbine blades, aero turbine blades, they are made of super alloys like Hastelloy, Vespalloy, Incalloy. mnemonic alloy. These are all some of the examples of superalloys that are used for manufacturing of the turbine blades. So those turbine blades, because this material is creep-resistant material. Now, the material being creep-resistant material, but the creep has altogether different phenomenon. Like the plastic deformation here has the movement of dislocation, but in case of creep, the deformation mechanism is not by the dislocation, it is by the grain boundary slip. So smaller is the grain, larger will be the grain boundary area, greater will be the slip, and hence the creep resistance will be poor. And that's why in case of engine materials, the main objective is not the refinement, but the main objective will be having a single crystal so that the grain boundary slip is minimized and the creep resistance can be enhanced, because the creep resistance, if you enhance, the material will deform less. Under tighter clearances, the material will work. So the single crystal casting for engine materials, and later advancements in the superalloys are coated with thermal barrier coating to reduce the temperature gradient inside the turbine blades. So these are some of the options available for the strengthening, both for the superstructure as well as engine materials. So these last two are the engine materials, and the top four are the superstructure materials. But the traditional route, though, have to comply with the strength ductility trade-off that actually puts a limit beyond which we cannot go any further. So this is this is what is just I spoke to you in my previous slide. So the superalloys. So the superalloys coupled with single crystal casting. The single crystal casting was facilitated by the directional solidification. So the turbine blades were cast, and the casting most commonly was the investment casting, and after investment, during investment casting, directional solidification, then evolved the single crystal casting. So this is how the Ni-based superalloys were developed from 1940 to 2010. Why I told 2010 is that in the very beginning I told that the high entropy alloy is the phenomenon of the last decade, 2011 onwards. So, but the next phase of evolution of the engine material will not come from the superalloys, but it will come from the high entropy alloys. What are high entropy alloys? I will just come to you with the next slide. What is novel about the high entropy alloys? I told you in the very beginning that the conventional alloys are dealt with the traditional concept of enthalpy, whereas high entropy alloys actually they deal with the entropy of mixing. What is that? The requirement, the minimum 5, as on today, the minimum 5 to a maximum of 13 different elements are already known to be mixed in order to make the high entropy alloys. But this 13 has no limit in finite, and hence we have a infinite workspace, infinite number of new high entropy alloys can be developed. So the space is very vast and open. Now, unlike in conventional material, there has to be a solvent and there have to be solutes. But in case of high entropy alloy, the principal element, that is the solvent element, can be either prominent element. So there is no limit. So high entropy of mixing, simple solid solution phase, lattice distortion. So what happens, because so many large number of elements are mixed together in the liquid and solid state. So because of the difference in the chemistry and the size of atom, there is a huge lattice distortion. That lattice distortion actually gives rise to high strength and high hardness. And when the temperature increases, the lattice distortions again rearrange and adjust, and thereby to maintain the hardness and strength of materials. So this is a typical high energy concept. You can see that A, B, C, D, E, 5 elements are mixed in a unit cell, whereas distorted configuration is on this side, on the right hand side. Future aeronautic materials lie not only in HEAs but also in graphene. You see the graphene is interestingly represented at that graphene can actually. I think only 5 minutes are left, 5 to 10 minutes will be left. So I will be signing off on time. So for that, till that point in time, please give us a little bit of attention. It will be just about to be finishing. So the graphene. So you see the pictorial representation of graphene. It is a very strong material. Young's modulus of the order of 1 TPa and tensile strength of the order of 1100 GPa. This is the strength. But the bulk use of graphene are yet to evolve. There is a long way to go for the graphene to be used for the bulk use, because so far as it can be only used in the form of particles and chips, microchips. But its bulk use has to, there is still a long way to go for its bulk use. The other advanced materials will be the advanced composites. What those advanced composites are there, that is my next slide will show, and the high entropy alloys. These are all the three most important aeronautical materials of future: graphene, advanced composite materials, and high entropy alloys. Advanced composite materials will be mainly for the superstructure, whereas high entropy alloys will be mainly for the engine, aero engine application. So they have two different domain of application. This is for the superstructure and airframe structure, whereas high entropy alloy is for the engine applications. This is what is the representation of different new generation materials. This is the high entropy alloy. Both are high. Strength and toughness. Typical trade-off between the strength and toughness do not exist, unlike the conventional materials. This is the max phase is another material. Max means M stands for early transition element, A stands for the later transition element, and X stands for carbon and carbon, oxygen and nitrogen. So this is the typical phase, max phase. This is another new material. Another one is the nano ODS, oxide dispersion strengthened materials. So, and the last one is the metal matrix composites and ceramic matrix composites. So these are all the materials that actually suit the requirement of the materials of future for aerospace applications. So this is actually the general representation of the future material that has to come. The future materials will mainly come from this class of materials. Okay, so what are all the properties of the high entropy alloys? Is that it possesses very high strength of the order of greater than 200 MPa or 2000 MPa, greater than that. And no conventional material is comparable in terms of the strength of the HES. Apart from strength, they have comparable ductility, as well as they have very good corrosion resistance and wear behavior. So all properties simultaneously get enhanced, and the traditional trade-off between strength and other properties do not exist in case of high entropy alloys. This is the, and of course, as the temperature rises, the strength and other properties of traditional materials reduce very sharply, Whereas in case of the high entropy alloys, there is the performance is steady. You can see these are all the different types of high entropy alloys with the different colors of geometric shapes, and you can see the hot hardness and temperature 1000 degrees Celsius hot hardness. The 200 at 1000 degrees Celsius, the material was heated and its strength was measured in hot state, and you will see that it maintains usually a steady hot strength. So this is one of the plots that depicts the relationship of hardness with the temperature. And again, this is the depiction of Young's modulus and specific strength of different high entropy alloys. This is actually reference. So what high alloys are? I think I have to skip this slide I already showed you. High entropy alloys actually you can see here the HEAs have a minimum of 4 to 5 components, and the maximum number of there is no limit for maximum number of components, but minimum 4 to 5 components. The alloy can generate uniform structure, either FCC, BCC, or HCP. You can see the example of cobalt, chromium, copper, Fe and I as the main components of the HEAs, wherein this particular alloy has a BCC phase, whereas the material such as Fe has a BCC phase and chromium has a BCC phase, whereas nickel and copper has FCC phase. And that too, in case of Fe, when the temperature rises beyond 901, it changes from BCC to FCC, and then again 1400 around, it changes from FCC to BCC, but the basic structure remains FCC. So there are 3 types of HEAs: BCC HEAs, FCC HEAs, and HCP HEAs. Out of these 3 categories of HEAs, the FCC HEAs possess the highest magnitude of the creep resistance. So this is what I just wish to show you. This is the structural schematic representation of atomic arrangement in unit cell. And now thermodynamically, this is the classic equation which governs the gives energy, free energy, wherein the enthalpy remains the major factor for the conventional alloy development, whereas in case of the high entropy alloy, this is the delta S mix is the main factor which actually comes into play. So this actually in order for the energy to be global minimum, we can actually play with this right hand side of this equation. Delta H should be low and delta S should also be low. So this is how we actually calculate. We can also calculate the gives free energy and then identify which particular alloy is most likely to be formed. That is what we do in FSP. We actually calculate enthalpy and entropy, and then utilize this as well as this equation to calculate the fraction of which particular HEA has been formed. So this is an equation. I think the time is about to finish, already finished, so I have to stop here. There are 3 types of high entropy alloys. One is the low entropy alloy, medium entropy alloy, and high entropy alloy. Basic categorization will be based on the delta S configuration. If the delta S configuration is greater than 1.5, it is high entropy alloy. Between 1.5 and 1, it is medium, and if less than 1, it is the low entropy alloy. The common stainless steel again is a medium entropy alloy. So हमारा 18.8 high entropy. This is what is the entropy of some of the alloys which are categorized as low entropy, and this is the medium entropy alloys. These are all the common materials. So you see that Ni based superalloys, they are the medium entropy alloy, whereas the HEAs are the high entropy alloys, so performance is better. Infinite, you can develop infinite number of new materials. So scope is so one of the most common ways of manufacturing the spark plasma sintering. You see this schematic diagram of spark plasma sintering. This is the raw material, which is blend of different alloying element, and it is pressed between the dies. The dies are of graphite, and then it is subjected to pulse current, and the pulse current actually softens it because of interfacial resistance, initially through resistance heating, and then when the current is increased, then that bridge breaks and the spark between particles takes place. Thereby, even melting can also occur. This is the typical specification of the spark plasma sintering parameters, and this is what is the characteristic. These are the advantages. The sintering time is reduced, the heating cycle is very fast, and grain to grain bonding is very good. Sintering temperature is very less. Temperature should be less, time should be high, that actually stops the grain growth, and the holding time is also very less. The total processing time is 20 minutes. Clean grain boundaries. So these are all the advantages. So there are two types of spark plasma sintering. First of all is the solid state. Next one is the fusion state. In the solid state, the main heat energy dissipation through the resistance of interfacial resistance, whereas in case of the fusion based, the plasma is formed between the grains. The other routes that are available is the powder metallurgy route. So again, in powder metallurgy route, in case of spark plasma sintering, the heating and pressing is simultaneous, whereas in case of the powder metallurgy, it is sequential. So this is some of the microstructures that have been obtained from the high entropy alloys. Then this is the various steps involved in the development of the high entropy alloy. First of all, we prepare the high entropy alloy, then we anneal it several times. Annealing is required sometimes 3-4 times in order to make it homogeneous and then characterize. The other technique for these is the coating. High HE coating is also employed, and HE coating is by powder injection as well as sintering by laser. So I finish it here, and I wanted to show you how we developed the HEA by FSP, but I believe time is not there, so I have to finish in between. Should you have any questions, you are most welcome, and otherwise I have finished.
Good morning, sir.
Good morning.
Sir, it was very interesting. Rather than this is the modern work what you did instead of that ancient one. But I have some doubt, not doubt. I want to clear some facts that during Chanukya era, some we convert one metal to other, like that preparation of gold from copper, like that. Is there
your voice?
Hello?
Is disturbed actually. No, I can't hear completely. Yeah.
Okay, I'll repeat again, sir. During the era of Chanakya.
Okay.
It is not, sir?
Yeah.
Chanakya, so that the manufacture of gold from the other metals like that work was going on. Chemical modification of the metals.
No, actually, no, I understand that. See, the thing is that I have shown only those material developments for which actually the archaeological evidences were found by me. I typed such a lot, but only those I included in my slide, like the iron pillar. It is very clear. So many more evidences have yet to come. Maybe carbon dating and all, many things are going on at the moment. So in near future, maybe some new things will come up. That's why I did not include. There are many. You are correct. But I could not find the citable references so that I could include in my slide. That's why I escaped. Okay. So that is there. Yeah.
Okay, sir. Sir, and another one, sir. This is like that Vimana Shastra, like from Bharatwaj 7,000.
Yeah, see the thing.
IIT Bombay.
No. Yeah, but that has to come actually, as a citable reference. See, I tell you one thing.
Yeah.
You mine through creep of glaciers.
Yes, sir.
You search on Google creep of glaciers. Several thousand of lakhs of weight of glacier shift their position by as great as 2 to 3 foot. This shifting actually changes the land and water line of the globe. So due to which, during several per year, 2 to 3 feet it shifts. So the land continents also shift. So over several thousands of years, it may happen that several civilizations would have gone down below the seabed. So that need to be excavated. And that work, until it comes up and available as a citable reference, I usually avoid. That is there, no doubt, but a lot of it need to be excavated and reported. Okay, that is there.
Thank you very much, sir. You collected a lot of it, sir. It was very interesting.
Thank you.
Any other query from participant side?
One to 6 room number.
Thank you. Siddiqee sir, thank you very much, sir.